Okay, well, thank you all for coming here. I'm very evangelical about hypernetworks, and I'm trying to persuade you that this is where we should be. So, I think it's true to say that everybody in this room thinks that networks are necessary, if not sufficient, to try to understand dynamics of social systems and complex systems in general. Is there anybody who doesn't believe that? So I would say that's a complete consensus. And what I hope to do, by the time we're finished, is to have the same consensus about hypernetworks. So I'm going to give you the hard sell, and I really do want to persuade you. If you don't agree, though, I would be delighted to hear your counter-arguments, because I can learn from that. So it's reasonable to ask, what is a hypernetwork? So we know about networks of similar people. We know that, for example, people who are what we call binge drinking in the UK, where people drink huge quantities of alcohol, that typically your friends tend to be people who drink huge quantities of alcohol. So that's interesting. And apparently it's true of obese people and people who play games and stuff. And what's interesting about this is that very many of the policies which are put in place for such things are targeting the vertices and not the network. So if you increase the price of alcohol, that's targeting a vertex. Whereas if you wanted to do something about binge drinking or obesity, if you take a network perspective, theoretical perspective, I believe you're more likely to be successful. So we have all that, and then we have these much more heterogeneous networks where you've got families and work structures and stuff like that. So we know all that. And we know that not only are the vertices heterogeneous, but indeed we have many heterogeneous relationships. And they all interact together, and it gets quite complicated. And the starting point for hypernetworks is that these relationships may involve more than two vertices. So here's some examples that if you have, for example, a meeting between three people, it's not the same as three meetings between two people. So something happens in the generality. The idea of the piano quartet is that you get when you hear a piano quartet, it's kind of a gestalt you hear. You don't hear the violin separately from the cello, etc. I mean, you can, but generally you hear it as a whole. And generally, if you have a team of 5 people, again, this is not a set of pairs of people. It's the whole lot of people working together. So that's the big idea between hypernetworks. And this idea that enemy relations are important, of course, itself goes back many years. But here's the starting point. We go from networks to hypernetworks, where we have enemy relations. And so this is an example that I give, which happened to me once. So that if you have pairwise telephone calls, so my daughter telephones me and says, Mum says I can have a new pair of red shoes. And so I say, okay, you can have a new pair of red shoes. Then, unbeknownst to me, my daughter phones my mum and says, Dad says I can have a pair of red shoes. And then the next thing is I get a telephone call from Mum saying, are you crazy? And that girl has too much stuff. But anyway, the daughter gets a pair of red shoes. If this had happened, that we had a conference call, that this trick could not work. So here's a very simple example of where the social structures are different, where 3 people participating together is clearly different from the pairs of things. And so we can generalize from the binary relations, which are very familiar to us, to 3-way relations and 4-way relations, and have nice algebraic ways of doing that. So classically, people have looked at this using hypergraphs, which are where the number of vertices is allowed to be greater than 2, but it's essentially a kind of set theoretic approach. So here's a simple example where you have a relation between these arches and the blocks that make up the arches. And you get a bipartite network from this, so every arch is made of a set of blocks, and every block has a set of arches which it forms. And so you get the first arch is this subset, that's another subset, and so on. So we get a class of subsets, and this makes this nice structure called a hypergraph with all its intersections. And so I call a Galois hypergraph this object with all the intersections. So hopefully that's all very straightforward and simple. As most of what I have to say is, and what's also interesting is if you look at the so-called instance matrices for these relations, you very often find these groups of ones where everything's related to everything else. I'll say more about that later, but again, that's quite an important idea in hypergraph theory, the so-called Galois connection, which I won't go into in detail. But you can imagine if you've got a set of stuff on the left here related to the stuff on the right, that's taking a left versus right perspective. If you take a right versus left perspective, you get a similar kind of structure. And so, for example, if you're interested in analysing text, which I am personally, then you've got things like words and phrases are related to concepts, and the concepts related to words and phrases are. And you've got the possibility of investigating text using these kinds of structures. And the same would be true with beliefs and opinions, etc. And this is what's really interesting, is you've got the possibility that this subset of people has that subset of beliefs, opinions, or words or concepts, or whatever it is. These are very tight bits of structure. Let me switch my own phone up, actually. I found just my phone. I apologise for this. Okay, just. That once happened to me, and I couldn't switch it off, so I had to throw it out of the room. And somebody came up to me afterwards and said, you're not capable of multitasking, which I was very insulted by, but it seems to be true. So here's one of the ideas, is that hypergraphs are lovely things, they have this lovely structure, but they are set theoretic, so the order of the vertices doesn't matter. And here you've got exactly the same set of parts, but they are assembled in a different way, and clearly they are different. So hypergraphs are great, but they don't have enough structure for the kind of things we want to do. So we want to go from sets to what are called simplices. So the generalization of an edge in a graph is a triangle, and the generalization of a triangle is a tetrahedron. And more generally, these so-called simplices are objects with sets of vertices in multidimensional space. So if you can imagine the tetrahedron, that's a nice three-dimensional thing. And importantly, these are conceptually different, but also the algebraic representation is different, and the algebraic properties are different. So I won't have too much mathematics today, but this is important because we can make these distinctions. And the important thing about a simplex is that the simplex B comma A is not the same as the simplex A comma B, so the order matters. So if you look at these things called simplices, the simplices have faces. I've got one yellow and one grey here, and these are interesting because the simplices can be connected through multidimensional faces. So in a network, you're connected through the vertices, 0 dimensions. In these so-called simplicial complexes, you can be connected through higher dimensional faces of the simplices. And that's very interesting. So a simplicial complex is a set of simplices with all their faces. So I like to give this example from the Gestalt psychologist Katz, really very old book, I think written in the 1930s, where he says that vanilla ice cream is not equal to cold plus yellow plus soft plus sweet plus vanilla. It is vanilla ice cream. And if you can represent this using a simplex, which is different to the set, so the set can actually represent these wholes, and that's a big step forward. And it then becomes clear that the simplex in the middle, the relational simplex, is not the same as the set of vertices, but it's also not the same as a clique. These are different kinds of objects. And so simplices are letting us do some more subtle representation than we can get using conventional network theory. Then we have these interesting structures about sharing q-dimensional faces, and so you get you can define things like the eccentricity. Things are more or less highly connected to each other, and you get things like these q neighborhoods, and you can look at this notion of q connectivity. So here you've got these subsets of simplices are connected through their vertices, which is different to them being connected through their one-dimensional edges. And the significance of this is that this underlying connectivity, just as in networks, can constrain the dynamics of the system. And so you have the possibility of some event here being transmitted through the shared face to another piece of the structure, being transmitted to the rest of it, but not being transmitted because the dimensionality is not sufficient to enable the connection. So that is potentially interesting. So you can imagine this in a committee structure, where if two committees are connected in a kind of low-dimensional way, then a person who sits on two committees may be inhibited by transmitting information from one committee to the other, whereas if it was one connected with two common committee members, then maybe they would support each other and feel more confident in passing information, or indeed, one of those people may inhibit the other from passing information. So these microstructures are really quite important. And so sometimes it can happen that you get the transmission, and sometimes it happens that you can't. You get other kinds of structures like all this. So what I'm showing here is another subtlety, which is you can have a chain of connections, so A affects B, and B affects C, and C affects D, etc., through these structures. But you can also have the possibility that everything is sharing something in common. So this is a really important structural property of systems. And so you can imagine these tetrahedra sharing a triangle, and to show that, you take it apart and put it back together again, and you have what I call a star-half pair. And again, these are interesting, as I showed you before, because you've got the two hubs are related to each other in this so-called Galois connection. And so here you've got a relation between animals and characteristics. They can be brown and quadrupeds, etc. And again, you get interesting combinations of these subsets where they're all sharing the same thing. If we look at these so-called Q connectivity, we can have a Q-dimensional graph, which is a nice thing. But again, the problem would be that the Q graphs can summarize this high dimensional connectivity, but there is a problem because the two objects at the top have the same graphs, which is a triangle here. And so there's something more subtle going on at that level. Perhaps I won't get too much into this, but again, you have these kind of, not exactly holes in the system, but like depressions and pieces of local structure, which themselves are also very interesting. I'll skip off on that, but this is what I said to you earlier, that if you take a relation between two sets, and if you swap the rows and the columns, you can get these so-called maximal rectangles, where everything's related to everything else. That's clearly a canonical piece of structure. And the great problem with this is that computing these things is incredibly expensive. So the combinatorial explosion is astonishing. And a nice thing about these, the Q connectivity relation is it's much more tolerant to local disconnections. So this rectangle I show you here is almost a perfect maximal rectangle, but not quite. And the Q analysis can help you find that. So this is where we can actually add to the conventional theory, the Galois theory, by the Q connectivity connection algorithms, which are better for the computation. Okay, now simplistic complexes are great things, but they're still not strong enough for what we want to do. So in this picture, I show you 16 sets of lines. The lines are the same, but they're all combined differently. So under relation 1, you get what's called the sun illusion, where most people see a white disk in the center, and that's interesting. And clearly that structure is very different from if you put the lines a different way, you get the illusion of a rectangle. So using this notation where you put the relation explicitly into the notation enables you to discriminate these kinds of things. And clearly, when we look at any kind of systems, we want to be able to discriminate things which are so clearly different. And this is a way to do this. And importantly, we must have a notation that can capture these differences, because ultimately we want to put these things inside computers, and the mathematical notation sits alongside data structures. So this is to show you one of my own favourite relational simplices. So if you take the vertices, you take gin and tonic and ice and lemon, if you put them together and you mix them in the right way, which is itself a great skill, then you get the perfect gin and tonic. And as you know, if you go to some bars that it's not mixed the right way, you get something which is not the perfect gin and tonic. So the relationship matters. And as you know, James Bond preferred his martinis shaken and not stirred, so it can be very subtle indeed. And here's some other structures which again show how important it is to be able to represent any relations in quite ordinary situations. So at the top we have the knight forking chess. So chess players know this structure. It's an obvious thing for them. But it's important that they can discriminate it one from each other. And underneath we've got the same atoms are combined in different ways, and they give you isomers which actually have different physical properties. So again, the combinatorial relationship between things really matters in these systems, and it also matters in social systems. So even simple things like IQ tests can be construed to be these relational simplices. I think you're all smart people, so you already guess what the answer to this is. But the point is that with this particular test, sorry, I don't have the answer to it, but essentially you've got the first one is the triangle and the circle, and the relation is the second thing is inside the first thing. And that's the same for the circle and the square. And so now we want to have the second thing, the triangle, being inside the square, so it's actually obviously B, which you all guessed. And so the IQ test is done. This is another example of a really interesting thing. So this is Richard Gregory's cafe wall illusion. And so most people, when you look at this, although these are perfect squares, that they bend in your perceptual system. And so again, it actually matters how they're put together. Because if I just shift them along a bit, then you lose that property. So here's another example that I like to think of these relational simplices like a balloon. So if you take one of the vertices out, it's like putting a pin in the balloon. The simplex collapses. So if you take away here you've got a cyclist, for which you need both a rider and a bicycle. And if you take away the bicycle, you don't have a cyclist. And if you take away the rider, you don't have a cyclist. So you need both of them. And the gin and tonic speaks for itself. So I define a hypernetwork to be, in the simplest case, a set of these so-called hypersimplices. And there's no competition between hypernetworks and hypergraphs and graphs and so on, because they're all, to my mind, beautifully integrated, as this diagram suggests. So if you take a graph, if you orient the edges, you get a directed graph, and if you put numbers on that, you get a classical network. If you allow graphs to have more than two vertices, you get a hypergraph. If you put more structure on, you get a simplicial family. And if you put more structure on with the relations, you get a hypernetwork. So for me, it's one coherent story. And what we're getting with hypernetworks is not a different way of doing it, but it's adding to what we can do with these tools. They've already proved to be very powerful. Now, one of the big problems in complex systems is that most systems have multi-level dynamics. And one of the big challenges we have is that we have theories of systems, and typically we have macro-level theories, we have micro-level theories, we have meso-level theories, and these theories are not formally linked to each other. And so you can have the microdynamics doing one thing, the macrodynamics doing the other, and you have no theoretical relationship between them. So to my mind, this is one of the greatest challenges in science that we have. So be it from biology to environmental planning, whatever it is, we have this problem that we have local theories, but we don't have global theories, and that's a big problem. And it's actually even not clear whether you can tease apart systems into these multi-level systems. in the way that this diagram suggests. So this is the reality of the complex systems, an absolute mess, everything's connected to everything else, and it's just very confusing trying to understand it. And some of us dream that we can actually tease it apart and get some kind of sensible representation. But I think it's an open question. So if we do it, it can be done. If it can't be done, then some of us have wasted our life trying to do it, but that's too bad. So if you look at systems, typically you take any system, if you look at this room, this is a very simple room. Now how many objects do you think are in this room?
A lot.
A lot. Okay, this is kind of counting 1, 2, 3 a lot. But there's probably even big objects like this.
It depends on the level of resolution.
Yeah. But
it can be thousands actually.
Yeah, indeed. Even at this level of resolution, there's many hundreds, if not thousands. And I once asked this to a class of students, and they said there's 50 million because of all our hairs and so on. So you're right. But the point is that when we look at systems, so you come in and look at a system, this room, it's a simple system. And it kind of depends on exactly the resolution, what it is you want to know, and what it is you want to say about it. But generally speaking, you've got the system, and you go in, you know nothing about it, or little about it. So you've got a kind of a soup of the knowledge you have, and the representation, it's all a natural language mess. And you're trying to abstract from that some kind of formal description or theory. And so I call this the intermediate word problem. We're trying to abstract the intermediate words with all their taxonomic structure and stuff like that in a way that will work and give us a sensible kind of story. So this is a kind of cartoon of what might happen if you went into a hospital. So you've got the hospital, and then you would realise that you've got departments, surgical department, paediatrics, etc. And we start building this language, this kind of ontology to describe this multi-level system. And so if you take a Hypernetworks perspective on this, if you take, for example, these 3 blocks, and you simply assemble them into an arch, then the arch has emerging properties which are not possessed by the blocks. It's a higher level structure. So this very simple idea gives us a way in, it gives us an arrow for multi-level systems. And my belief is that this is important and necessary for what we do. So if you assemble vertices into high-level structures, you've actually moved up the hierarchy of representation. And so that's fairly obvious. And if you've got numbers on the vertices at the lowest level, they will aggregate up in various ways. Now, what's something interesting in multi-level systems is that we know that we have taxonomies, so that Labradors and Poodles belong to the class of dogs, and dogs belong to the class of animals, etc., etc. But actually, what happens in reality is it's not just taxonomic hierarchies, but interweaved with them, we have these kind of hierarchies of assembly. And so as I show here, you have what I call an AND aggregation, where you need this part, and that vertex, and that vertex to make the whole. Whereas if you go from what I call the OR aggregation, any one of these arches is sufficient to have an arch. So these things are interleaved with each other. So we have these kind of ontologies with these interleaved kind of structures in them. Now, people talk about reductionism, and reductionism is supposed to be very bad. But actually, I think reductionism is in our brains. So if you take something very simple like these 2 rectangles, R1 and R2, and you put them on top of each other, then something, to my mind, really amazing happens, which is you get the thing at the top, but then your brain creates new stuff. So the little square I've just made isn't part of the rectangles, it's been manufactured somewhere. And so we go up this hierarchy assembly, we come down, and we can go even further down. Now you see lines inside this structure. And then we start building stuff up again and getting new things. So this manifestly happens, this is what we do. And my own belief is that when we look at systems, we have this kind of top-down, bottom-up view of it all the time, and we see the whole system, and we see the parts of the system, we see the assemblies and so on. I think that's one of the reasons that we are successful in representing things. So that, I think, is important, because if we want to have models of complex systems, then I think this kind of process is going to happen. And we need our machines to be able to take in information at macro level and micro level, and to do the construction and deconstruction, so that we're building these intermediate representations. Because other things being equal, we can't keep on doing this stuff by hand. We need to automate this process. And so I already showed you this example. I want to give you another idea now, which is the notion of backlogs and traffic. So with a network, for example, you can have a network which may or may not have stuff flowing through, yeah?
It means backlog.
I'm sorry?
Backlog, what does it mean?
Yes. The backlogs in English, if you go to a play, so if you go and watch a Shakespeare drama, then at the back of the stage there will be a piece of canvas which may be painted with a forest. And so this is the backcloth against which the action takes place of the princes arguing or whatever they do. So the idea here is that if you've got a network structure, that acts like the backcloth, which supports the action of the system represented by numbers. So typically if you have traffic flows or flows of communication, telecommunication, etc., the network is supporting that. And of course, if the network breaks down, the dynamics break down. And so we generalize this that the hypernetwork is this, these structures of hypersimplices with all their connectivities, which are supporting all kinds of dynamics of the system. And you've got the so-called traffic is the fast stuff, which is moving around the system very fast. And the backcloth is relatively slow. So that, for example, if you take a cathedral, it takes a long time to build a cathedral, but then every week you can have different numbers of people come to worship in the cathedral. So this is the general idea. So here we have a piece of structure like a company. We have these various capabilities. We have some emerging capabilities, so that I by myself cannot make a car, but me, the same with lots of other people and lots of other skills, could make a car, and that happens. And we have these numbers, these patterns of numbers flow over the structure, and they're all very important. So we, just simple things like how much we're all paid, how much the department has to spend, or whatever. These are all the things that we're trying to manage. And the generality is that we have this black cost structure, which in this cartoon I show by these simplices here. And then you may have chaotic dynamics, and you may have all kinds of surfaces and stuff like that. And the dynamics represented by numbers are related to the dynamics of the relational structure that supports it. So this would be true, for example, in opinion dynamics. And so these two people are perfectly happy, they have consistent worlds, and they know what they think. But they may think different things. And if they have inconsistent beliefs that you can't believe A and not A, actually that's not true, you can, but it's stressful. And so that creates a stress in the system. So if I want to believe what my friend believes, I've got to do something about this other belief, which is not fitting. And so I can connect up better, but I've got this internal stress, and ultimately it's better to get rid of it. And now I'm happy again. So I've stopped believing in creationism, and I started believing in evolution, or the other way around. And again, when we're looking at complex systems, looking at things like agent-based modeling, this is what we do at the micro level. So we have discrete interactions, and part of the theology of complex systems is that the macroscopic behavior emerges from the interaction of lower level stuff. So we all believe that. And so we understand that these are discrete interactions. And as we go up the hierarchy of representation, we start counting stuff. And we end up with numbers, so we end up with time series and stuff like that. And in some series, in some systems, you can predict or understand the future from the time series itself, but in many systems you can't. So the time series itself emerges from lower level dynamics, and you cannot know what the time series is going to do without looking at the lower levels in this kind of way. Another interesting idea about complex systems and hypernetworks is that when you look at physics, physics is kind of tautological, so time in physics is measured by physical events, and the whole thing fits together very nicely. So the pendulum goes tick-tock, tick-tock, and you measure events by the pendulum, and then all the dynamics falls out. So we're very comfortable with that. It's the case in social systems that you have a different kind of time, which is system time, which depends upon the construction of bits and structure. So, for example, if you get married, life changes. That's a big event in your life. If you have children, if you graduate, you buy your first car, whatever it is. It doesn't matter if you do these things whether you're 17 or 70. Life changes the same way. And so actually in social systems, the dynamics is partially determined by these structural events. And so, for example, if you're building a bridge, you can't cross the bridge until the bridge is built. And so if the bridge is being built behind schedule, then you have to adapt your behaviour in clock time for system time. So that's important. And again, the dynamics of these systems, the time of these systems, you're trying to match the system dynamics with clock time dynamics, which are different things. And it's very important because we human beings, our lives are governed by these structural events. When you've just written your last book or whatever it is, that's a big event. And typically we celebrate events with champagne and the rest of it. Yet the problem is we consume resource in clock time. So we're paid by the month, our rent is monthly, etc., etc. And so we're constantly trying to adjust these two different kinds of dynamics. And that's a problem we have to deal with. And so again, this is another kind of cartoon which is saying that the connectivity structure at the low level constrains the dynamics at the low level. And as we move up this hierarchical representation, we get different ways of looking at those dynamics. And the point is, you need to look at all of it. If you've got a complex system, you're not going to understand it by modelling the macro level and ignoring the micro level, or vice versa. So I talk a bit about global system science now, following on from what we talked about at lunchtime. That global system science is a different way of talking about complex systems, but I think it's interesting because one of the things that we've learned in the last 10 or 20 years is that the world is highly connected, and so the financial crash was a wake-up call for economists, because economists don't behave like economists say, but they behave like systems behave, with lots of interactions between things. And so many things happen at a global scale, like climate change and economics and certain politics and stuff like that. So I want to talk about these various things quickly. So global system science, it can mean worldwide, but it can also mean local. So the nice example of this is cities. So cities have their political management done by the mayor and other people, which is looking inside the city. But cities have intercity dynamics, so that the cost of property in Paris is related to the cost of property in London and things like this. So we have systems of systems, and if you have a complex system, the question is, what are the subsystems and how do they interact? Are they necessary to predict the dynamics of the whole? So we have this notion of policy informatics, which is the use of computers to support policy. I personally like this notion in global system science, and I like this idea of policy informatics because it's taking those in the complex systems community to the reality of applying this science for real problems, of which we have plenty. And to apply the science, we must interact with policymakers. And to date, the relationship between scientists and policymakers is not as strong as it should be. And this is an issue in the European Commission, here in Brussels in particular. So this is a kind of bit of my catechism, really, my evangelism, that I say that policy is designing the future. So when you design anything, in principle, you go from a system which doesn't exist, and you hypothesize a system that might exist, and then you think of a way of going from where you are to where you would be. And I claim that policy and science and design, they're all entangled. This is the science of social systems. I think you cannot have you cannot have a social science without looking at policy. It's personal belief, and I think you cannot have policy without design. And I think understanding this entanglement is really important. So here we had the example of the intermediate word problem for that management system. What's really, really interesting about design is that you have two cycles. You have the generate, evaluate cycle. So you think, I've got a problem, here's a potential solution, is it a good solution? No, it's not, I'll try again. You generate more solutions. And typically in design, you find that the constraints that you're working against, you cannot find a solution that you're happy with. And typically what you do is you go back and you change the constraints. So for example, if I want to build a house for €200,000 and I want 17 bedrooms and 2 swimming pools and a tennis court, then I discover there's no solution. I talk to my architect and he tells me to be more realistic, and I end up with maybe 2 bedrooms and a garage, or no garage and 3 bedrooms or whatever. And so I'm changing the constraints, but the point is I'm changing the problem. So design is not like a mathematical problem where the problem is fixed and the solution comes from it. So design is a co-evolution between what you think you want and what you think you can have. And I think that's the way that human beings solve problems. I think design exemplifies this, but this process I think is common to everything. And the important thing about design is that it's actually not a cycle. They're much more like helices through time. Because every time you go around these design cycles, you collect more information, you collect more knowledge, more understanding, you do more experiments until eventually you've got an understanding of the system, or the system you're trying to create, where you're ready to execute and to implement it. And so again, this the design is typically multidimensional, that you identify subsystems, components, you know they're going to interact, but you still do it, you think about them in isolation, and then you move up and down the hierarchy until eventually you have some feeling for the whole which you can make. So now looking at policy, I would say that when you have a policy intervention, so you say, if I do this to my system, it will have this result. So if I build a block of flats with 1,000 apartments in it, then this will house so many people. And that's what I predict. And so I'm really saying if I give my system a kick from where it is now, it'll end up at some target stage in the future. So that's what we do. That's life. We must do something. We just kick the system and we hope it goes where we want it to. And the reality is that every time we kick the system, something happens and the system is knocked off trajectory. Well, that's actually very important because if you're a scientist, and particularly if you're a scientist that comes from a physical scientist, you have a belief in prediction. So you believe that the world can be predicted, which of course, in some cases it can, and in some cases it can't. But when we do policy, we are forecasting or we are guessing or we're doing something about the future state of the system. We're trying to be rigorous in our thinking so that the outcome is as close to what we want as the better. And we really don't have much science to talk about this kind of trajectory for systems where the town hall will knock or the government will have new laws, or the money will run out, or some act of God, and so it goes on. And importantly, how could you even test the notion of prediction in such a system when you say, if I do this to the system, it's going to end up at this target stage, but I know it'll never end up at the target stage because something else will happen to knock it off trajectory. So the whole question of what it means to make a prediction and the whole issue of the statistics and so on is completely different for these kind of systems. So just to give, I'll do it for time, I've got an end. So here we had, in 2011, we had the street gangs in London, and they caused mayhem and burnt down a lot of shops and so on. And we had this notion in the London riots that there were gangs operating. So it wasn't just people who were frustrated, the ordinary person, but there were criminal gangs doing criminal stuff within this kind of system. So we have this problem with street gangs in UK. I expect you have it here in Brussels and elsewhere, where the kids, they come together and they act in criminal ways, in antisocial ways, and so on. And this is obviously some kind of social structure, some kind of social behaviour, and governments care about this. So we've had a lot of work done on this in the UK, I'm sure the same elsewhere. So this is a quotation from some government report. That, so it said, one thing the riots in August brought home that we have a serious problem with gangs and youth violence in the UK. And so we're now looking for policy to do something about this, to stop this. So how can we kick this system so that we have nice, well-behaved young people who are living wholesome, fruitful lives? Well, this is these statistics for the UK. Again, I'm sure this is pretty true across the Western world. So of course, the most admissions to hospital typically are young men, for obvious reasons. They get themselves into trouble. But also it turns out that in the UK at least, the ones who are most admitted are those from the most deprived homes. So you could draw your own conclusions.
What is on the horizontal axis?
The horizontal axis is, what is this? This is, I think,
Age? Looks like age.
Yes. Yeah, but
it's
it's 13 to 14 years old. What does it mean? The 13 to 14 years old are the perpetrators and these are the victims?
It means that when people go to, in the UK, we have these emergency centres which anybody can go to and they will be treated. And so if you're a young man and you've just been in a fight, in a knife fight or anything like that, and you go to hospital to get fixed. And so these, you don't have a motor accident, you go to hospital. These figures count this. And so yes, as you show that this young men from 15, 16, 17 have the most of these kind of traumatic problems, which is presumably something to do with being a human being. But, some elements of biology and some elements of society. But anyway, this is what it's like. And again, the government would like to have policies to do something about this. So these various reports say, this is almost unbelievable. But in the UK, we had a policy where the police would identify the gang leader and remove the gang leader from the system with the belief, just like I said, you put a pin in the balloon will deflate and the gang will disappear. Of course, that's not how it worked. And if you take away the leader gives some kind of relational structure to those people. So you've got these, 10 violent, dangerous people who are being controlled by the gang leader. You take the gang leader away, and it's actually mayhem because they're struggling for power and so on. And so that particular policy caused much more trouble than it actually saved. And so you can see, look at this from a hypernetwork perspective. So there's the gang leader, and you remove him, and then you've got a kind of chaotic system. As the hypersimplices are breaking down and reforming, you get this highly dynamic situation. Now, this is another example, it's a very sad example of a gang member. So essentially, this person at the age of 0 years, their future is mapped out in front of them. So this young man, he's born to parents who are drug addicts, who there are many visits to the health centre and so on, that as you go through his life, he's got aggression at school. He's misbehaving at school. He's not fitting in at school. The school structures are all wrong. Increasing levels of violence, his truanting and so on. And as you go through this, he joins the local gang, he gets involved in drugs, and at the age of 21, he kills somebody. And now he's in jail for the rest of his life. So this is it's a very sad story. It's not an unusual story, but it's a structural story that the policy has to understand how these structures are forming. How is it that a baby is born to parents who are drug addicted and are criminal, and etc. So you may have your own partial answers to this, but if we're ever going to solve problems like this, we need to understand the micro-level structures which are forming these kinds of dynamics. And And I argue that we need this kind of relational theory to represent it. It is very complicated. To get all that data put together is difficult. So this is the story of these hypersyntheses emerging, and this is a precursor to the murder, which then ruins this person's life if it wasn't ruined already. And it's very similar to a kind of social chemistry. So chemists don't ignore the fact that the way that the atoms are connected are important. It's profoundly part of chemistry to know that these things are not the same. And so I would say that in social systems we have the same kind of social chemistry. We even use the word chemistry to talk about social systems. But we need to be able to represent it. If we're going to go from just a kind of qualitative verbal descriptions into ways of representing these systems in ways that we can collect data and investigate the dynamics, understand the dynamics, then we're not going to get this understanding. So my conclusions are this, that certainly networks are essential for analysing social systems policies. So system behaviour emerges from the interaction of the pairs, the network is the backcloth to the dynamics, and networks are necessary, if not sufficient, for a science of complex systems. And underneath it, I just generalise this. I say that hypernetworks are also essential for social systems and policy. Again, the system behaviour emerges from the NRE interactions, but again, the hypernetworks form this backcloth to these multi-level traffic dynamics. And so my conclusion is that hypernetworks are necessary for this science of complex systems. So this is my evangelical speech from the pulpit, so to speak, and I hope that all of my flock are now converted. Thank you.